In contrast to the method of parallelization we looked at in the last video, a second approach I find myself using a lot is to split the computing task into multiple smaller tasks and send each as individual compute jobs that run simultaneously. This can be an effective method for achieving high levels of parallelization, but might require a bit more effort to implement. One way is to write a script that contains a for loop that iteratively creates and submits a series of individual jobs. Think of it as one master script that creates and sends a whole bunch of individual scripts to the compute cluster. Again, we'll stick with the example we used in the previous video on loops of aligning 5 FASTQ DNA sequence files to a reference genome with the software Bowtie 2. In that video, we used a for loop to align the 5 files in succession, one right after another, without having to submit the commands separately each time. But if we have 5 different processors available on a high-performance compute system, we don't have to wait for each to run in succession. Instead, we can send all 5 alignment jobs at once, each to a different processor. The Owen supercomputer I'm working on here has well over 20,000 cores or processors distributed over around 800 different nodes, so there's lots of opportunity to run parallel jobs in this way. I'm first going to put the job script from the previous parallelization video here on the left side of the screen for reference, but for now I'll change it back from using 6 processors to just 1. We'll use this as a basis for a new script that will parallelize the task of aligning all 5 files by sending them as independent jobs. We'll use the echo command as part of this new script, and since we haven't talked about it in previous videos, we'll take a quick look at it here. At command line, echo basically does what you might expect a print command to do. It prints, or echoes, whatever you tell it to. So, echo hello world prints that phrase to the screen. Like all other commands, we can redirect echo's output to a file with the right pointing arrow or greater than symbol, and that'll be important as we construct our new script. So, I'm going to open up a new blank text file with Nano. I'll call it firstparallelscript.shell. And start with a loop that iterates over the values 1 through 5, corresponding to the 5 input files. For each iteration of the loop, I'm going to write commands just like I would if I were writing a typical job script, except I'll include them within echo statements. So, the PBS directives go at the top of the script, followed by the actual commands to run, in this case, the same Bowtie 2 command we ran before. One aspect that can be a little tricky here are quotation marks, when to use them, and whether to use single quotes or double quotes in a given case. Putting things in single quotes causes the text inside to be printed literally. This is probably a good idea for a lot of what you'll do, with one common exception being when you're working with a variable that needs to be interpreted, for example, the I in this loop. In those cases, you'll want to take it out of the single quotes. Double quotes allow for expansion or interpretation of variables, but just leaving the variable without any quotes generally works too. You can certainly put effort into learning the rules for quoting in Bash, but simple trial and error will probably get you there too, and itself is often an effective way to get a feel for how these work. Once the commands are written, I'm going to group them together by wrapping them in a set of parentheses, and then redirect all of that output to a new file. I'll call that new file alignmentjob$i.shell. Let's save the script at this point. I'll do that in Nano with Ctrl+X, then confirm I want to save with Y, and hit enter to use the current file name. Now I'll run that script. I can try with // the name of the script, but in this case I get an error, as I don't have executable permissions for that file. I'll use the change mode or chmod command with the +x argument to add executable permissions. I try again, and this time the script runs. Listing my directory contents, I see the 5 new job scripts that were created. Looking at the contents of the first one, the PBS directives are at the top, and the commands I was expecting for file 1 follow. File 2 looks similar, with the exception that the commands are customized for input file number 2. So, we created the 5 separate job scripts, but we didn't submit them. I'll reopen the main script in Nano and add one additional line at the bottom that has the qsub command, which, like we talked about before, in the PBS system is the command that submits the job to the compute cluster. I'll save the edit and try running this again, and this time not only are the 5 scripts created, but each one is sent as a separate job. This means that, assuming there are 5 separate processors available when they're created and sent, they can all run at the same time. The two approaches to parallelization we've looked at in this and the previous video can easily be combined, simply by including the instructions to run the software in parallel into the loop that writes the individual job scripts. Remember that you'll need to change the ppm value in the PBS directives as appropriate for each individual job, and then add a command line argument to tell the software to execute a parallel job, just like we did in the last video. Next, we'll wrap up this set of videos that introduce high-performance computing by taking a look at some ways to move files on and off remote systems.